In problem number 12, we have the limit as x approaches 0 of sine of 1 over x. And using the properties of limits, this could be rewritten as sine of the limit as x approaches 0 of 1 over x. Remember, with function composition and evaluating limits of function composition, we take the limit of the inside function and simply evaluate the outside function at that limit. However, limit as x approaches 0 of 1 over 0 is going to be infinity. The function 1 over x, y equals 1 over x, looks like this, and as you're approaching 0, actually from one side you go to positive infinity, from the other side you go to negative infinity, and there is no limit as sine approaches positive infinity or negative infinity. It doesn't exist. This is the classic example of limit not existing due to oscillation. And we'll go on to problem number 13. In 13, we have the graph of y equals x squared minus 9 over 3x minus 9. And we're asked where vertical, horizontal, asymptotes, removable or infinite discontinuities exist. We're always going to try to factor and cancel here. The numerator factors as x plus 3, x minus 3. The denominator factors as 3 times x minus 3. The x minus 3 factors cancel, leaving 1/3 times x plus 3, as long as x is not equal to 3. And so this tells us the fact that the factor x minus 3 canceled completely from the denominator tells us that we have a removable discontinuity at x equals 3. There are no more factors in the denominator that would become 0, so there are no vertical asymptotes, there are no infinite discontinuities, and since this function is essentially 1/3 times the quantity x plus 3, it's a linear function and there is no horizontal asymptote. 14, the limit as x approaches 0 of sine of 5x over x. This is very similar to our important limit as x approaches 0 of sine x over x, and we've continually stated that as long as we get the same value inside the sine and in the denominator, then that limit would become 1. So starting with limit as x approaches 0 of sine of 5x over x, we would need to get a 5 in the denominator. But to do that, we'd also have to multiply the numerator by 5. And when we do that, we get sine of 5x over 5x. That limit is 1, just as the limit as x approaches 0 of sine x over x is 1. And 1 times 5 would be 5. Similarly, limit as x approaches 0 of sine of 4x over x would be 4. And the limit as x approaches 0 of sine of 3x over x would be 3. In each of these cases, we would find this answer by multiplying top and bottom by 4 or by 3. Then the sine of 4x over 4x, limit as x approaches 0 would be 1. 1 times 4 is 4. In the denominator, sine of 3x over 3x would be, limit as x approaches 0 would be 1, times 3 would be 3. We'll go on to problem 15. In problem 15, we have the limit as x approaches 0 of 4 minus x squared over x squared minus 1. Now you have to note that this is a limit at infinity, and so we're interested in the degree of the numerator and the degree of the denominator. Since the degree of the numerator is a second degree, and the denominator is also a second degree expression, then we want to take the ratio of the leading coefficients. And even though 4 is the first number, the leading coefficient would mean the coefficient of the x variable with the highest power. So we really should rewrite the numerator as negative x squared plus 4 over x squared minus 1, and we're really concerned with negative x squared over x squared, so the horizontal asymptote would be negative 1.